Hi kids, this slideshow is on the first two circuit equations, the fundamental ones, Ohm's law and the power equation. So when you're building a circuit, there's really only two things that are in your control. You can control the resistor and you can control the power source. And modifying those two circuit components is how we can adjust the values of the variables throughout the entire circuit. The voltage is determined by the battery or the power source. And it turns out that almost many of the batteries that you guys use in your everyday life actually have the same voltage, because the voltage is determined by the specific chemical reaction that's happening inside the batteries. There is a very common pair of chemicals that's cheap to manufacture and non-toxic relatively, and that's what you find in all of those round batteries, the AA, AAA, D, all of those things have the same chemicals in them, which means they all actually are 1.5 volt batteries. So the chemical reaction that happens transfers 1.5 joules of energy to each coulomb of electrons that passes through. So if you wanted to increase the amount of voltage in the circuit, well, it's not just changing a AA out for a D because they have the same voltage. The easiest way, or the way that typically it happens within your devices, is that you just string multiple batteries head to tail, because each one of those batteries is giving 1.5 volts. So if by the time I've gone through 3, now I've gained 4.5 volts. There are some different batteries, like lithium, that just has a different chemical reaction and gives a different amount of energy to the electrons that pass through. So changing the voltage of a circuit, a battery-powered circuit at least, is primarily done through changing the battery. The second thing you can control, of course, is the resistance. Each device has a sort of natural resistance that is determined by the materials and the design of the device. If you wanted, for some reason, to have more resistance in your circuit, you could add something like a regular plain resistor that we talked about in that first slideshow, that just sucks energy out of the circuit without doing anything else. Or you could change the design of the device. You could pick a device that had a lower resistance. Sometimes changing the temperature of the device can adjust the resistance. But in general, if you're wanting to try to change the resistance in a circuit, you got to focus on the resistor. So given that, it should make sense that voltage and resistance are typically independent variables. Their values depend on the hardware in your circuit, and changing one of them doesn't change the other. So if I double the number of batteries in my circuit, it doesn't change anything about the resistance of the circuit. The only way to do that is by tinkering with the resistor. The other two variables, current and power, are going to be the dependent variables. You can't really adjust those on their own. The way you adjust those values is by tinkering with the voltage and the resistance of the circuit. And when you change voltage or resistance, both current and power are going to change as well. And we'll talk about the relationships that impact how those variables change in the following slides. So if you had a plain old circuit with one light bulb and one battery, and you wanted to change the amount of current flowing through that circuit, well, the first way you could do that is by increasing the number of batteries. Right? It should sort of make sense that if you give each battery or each electron more energy, more electrons are going to be moving through the circuit as well. So increasing the voltage is going to increase the current. That means that current has a linear relationship with voltage. The second thing that you can do to impact the current is to change the resistance of the circuit. If you put a larger resistor in there, a higher resistance value, and the resistance of the circuit goes up, the voltage from the battery is able to push less electrons through the resistor every second. So for the same amount of energy, the current has to go down. That means that current has an inverse relationship with resistance. These two relationships combined to derive an equation known as Ohm's law, which is really the biggest one in electrodynamics. You use it on almost every electrodynamics problem. And since we know current has a linear relationship with voltage and an inverse relationship with resistance, Coulomb's law is I equals V over R. You see the linear and the inverse in that equation. If you bother to go and figure out the units of those things, you're going to find that they are internally consistent as well. The second equation that we'll be using all the time has to do with electrical power in our circuit. You'll remember that power is the change of energy every second, and this could be at the power that is being changed from chemical energy into electrical energy at the battery. That would be known as the power provided from the battery or at the battery. Or this could be the electrical energy being transformed into other types of energy at the resistors. And that's sometimes described as power used at the resistors. In general, the reason we care about it is because more power at the resistors means more light, more sound, more toast, whatever your resistor is doing every second. So generally speaking, the goal is to have an adequate power output at your resistor. So we really do need to know how to calculate power and how to control it. So if you wanted to increase the amount of power coming out of one of your resistors, the logical two ways to do it are, number one, having more electrons going through that resistor. If there's a larger number of electrons and they're transforming their energy at that resistor, then you're going to have more total energy going into the resistor. So there's a linear relationship between current and power. Or you can increase the amount of energy that each electron is carrying with it through the circuit, the voltage. If each electron has more energy to deposit, then it stands to reason that there's going to be more energy transformed at the resistors as well. So there's a linear relationship also between voltage and power. So to derive the power equation for circuits, we've got those two relationships, two linear relationships, which leads us to power equals I times V. This is the format I prefer to use this equation in because I think it's easiest for me to kind of conceptually picture where the power comes from. But if you take Ohm's law and combine it with the power equation, you can get two other permutations of that equation, which are power equals V squared over R or power equals I squared times R. And those may be found on your equation sheet as well. Just for fun, double check the units of power. If we've got that first equation, I times V, coulombs every second times a joule every coulomb, what happens is the coulombs cancel out and we're left with joules every second, which of course should be the watt. This is the end of this slideshow, so hopefully this has brought back some stuff that you learned a couple years ago or taught you some new stuff, and hopefully we'll be ready to jump right into circuits when we get going with class next time. Thanks for watching.